In the Atomic Revolution Part 1, we learned about the pioneers of atomic research. Now let's get into the details of fission, fusion, and all the rest. We're reading a 1957 book called The Atomic Revolution. In the symbol of the atom, the outer curved lines represent tiny droplets of electricity called electrons. These surround a central core in much the same way that the planets surround the sun. All common chemical reactions, such as the burning of coal, the rusting of iron, and the explosion of TNT, involve changes in these outer fringes of atoms. No such reaction touches the core or nucleus. Yet it is here that nearly all of the might of the atom is concentrated, and from here comes atomic energy, frequently called nuclear energy. Or by certain presidents we've had, nuclear energy. Yes. Atomic energy can be released from the nucleus of an atom in one of two ways, by fission or by fusion. The atomic cores of three substances, uranium-233, uranium-235, and plutonium, can most easily be split in two. In this process, called fission, very small amounts of matter are converted into very large amounts of energy. This conversion takes place according to Einstein's formula, E equals mc squared, which means that the energy produced equals the mass destroyed times the speed of light squared. In fission, each splitting atom releases several tiny particles called neutrons, which, if they strike other fissionable atoms, will cause them to split and fly apart. If enough U-233, U-235, or plutonium can be assembled in one place, an atomic chain reaction can be set up, in which the neutrons released by each splitting atom will split others. This reaction takes place in a fraction of a second in the atomic bomb, and relatively slowly in the atomic reactor. Only one of the three easily fissionable materials is found in nature. This is uranium-235, which comprises 0.7% of natural uranium metal. Uranium-233 can be produced, however, by exposing the metal thorium to the neutrons created by a nuclear chain reaction. Plutonium can be produced by the same means from a prevalent kind of uranium called U-238. And now, fusion. Fission involves splitting an atomic nucleus. Fusion involves uniting two nuclei. The substances most easily fused are hydrogen atoms of a special kind called hydrogen-2 and hydrogen-3. In a typical fusion reaction, two atoms of hydrogen-2 with a total atomic weight of 4.028 can be fused into one atom of helium with an atomic weight of 4.003. The difference in the two weights represents matter that has been changed into energy in accordance with Einstein's formula, E equals mc squared. Unlike fission, which is caused by neutrons, fusion is caused by extremely high temperatures, approaching those in the sun. Once a fusion reaction is started, it will generate enough heat to keep itself going for so long as fuel remains available to it. The problem is to start it. With the invention of the atomic bomb, men were able for the first time to produce temperatures on Earth that were sufficiently high to start a fusion reaction. As a result, it became possible to develop a hydrogen bomb, the first use of fusion. Now, scientists are trying to develop methods by which fusion reactions can be started and maintained in a slow and controlled fashion. When they succeed, it will then be possible to harness fusion, like fission, for creative purposes. Construction began on an atom-sifting plant at Oak Ridge, Tennessee, in 1943. The plant was designed as a mile-long series of sieve-like barriers through which uranium in the form of gas was to be pumped. In this way, the barriers would sift out explosive U-235 for use in an atomic bomb. A second job was to construct a plant to change uranium into the newly discovered easy-splitting element plutonium, also vital for bombs. The plant at Hanford, Washington, would consist of atomic reactors and chemical separation facilities. In all, the Manhattan District cost over $2 billion. From mines deep in the Belgian Congo came much of the uranium needed by the great plants at Oak Ridge and Hanford. Every ounce was hauled out through more than 1,200 miles of rocky canyons and steaming jungles, then shipped 5,000 miles across submarine-infested seas to the United States. Meanwhile, guards patrolled the borders of the secret Mesa Top outpost of Los Alamos, New Mexico. Here, scientists labored desperately to design the bomb. Finally, on July 16, 1945, the work of the Manhattan District was put to the test. Observers waited tensely in the desert as the seconds ticked by. Then, just before daylight, they saw the darkness ripped by an incredible light. The atomic device had worked. Just 20 days later, the Japanese city of Hiroshima was almost completely wiped out by the first atomic bomb. 3 days after that, the second atomic bomb burst over the city of Nagasaki. 6 days after that, the Japanese surrendered. With peace, American doctors and nurses joined Japanese medical personnel in treating the injured and studying the effects of atomic radiation. Oh, gee, that must have been fun. These were civilians, you know. Growing up in America and hearing this history in school, they really downplayed that fact. But yes, America dropped these bombs on civilians. But hey, we sent doctors. In the next installment of this video series, we'll get into how the military and the politicians cooked up the Cold War. Now, I lived through that, and I can tell you that it very much lived up to its name, Cold War, a bleak, depressing time of low-key hatred and vague fear that took its toll on all of us. Lots of our politicians and military leaders today are doing their best to bring that Cold War back right now with their attitudes toward Russia and China. The politicians and military do really well with a Cold War going, and they care not one whit what a Cold War does to the rest of us. So anyway, next time, we'll look at that.